All right, so one more video. In this video, we're going to talk about rational zeros theorem, which is a really cool theorem. Let's jump right to it. All right, so this is a cool theorem to know. That's very useful. Okay, so let's say you have a polynomial with integer coefficients. So let's say C0, C1, all the way up to Cn are integer coefficients in such a way that the C0, the constant term, is non-zero, because if the constant terms is equal to zero, then zero is immediately a root of this polynomial. So this theorem is trivial. And the leading coefficient is also non-zero. So if the leading coefficient is equal to zero, then it's actually a lower degree polynomial. So you then make sense to talk about the Cn to begin with. You could just have a shorter list of coefficients. So let's say we write down a polynomial this way. So C sub k corresponds to the integer coefficient of the kth order term in this polynomial. So you have a polynomial with real numbers with integer coefficients, and you want to see if there's like a really easy root to find of this polynomial. In general, that's difficult. So if it happens to be quadratic, then you could use quadratic formula. But if it's cubic or higher, it's not as easy to find the solutions. So it would be nice if there's a quick way to check if there's a rational solution to the polynomial. And this theorem will give us that. So if you have a rational solution that could be written as p divided by q in lowest order terms, then it turns out that when you write that rational number, the numerator has to divide the constant term, and the denominator divides the leading coefficient of the highest degree term. Okay, so let's look at it. So if p divided by q is a root of this polynomial f, then you could plug it in place of x. So we plug in p divided by q into that polynomial, and here's the equation we get. So the coefficient times numerator to the kth power divided by denominator to the kth power. So we're going to simplify this a little bit by multiplying both sides of the equation by q to the nth power. So on the right-hand side, q to the nth power, if you multiply 0 by anything, you still get 0. But you will, you can get rid of the denominator powers. Okay. So if you simplify, you'll get this equation here. So you multiply by q to the n, but you still dividing by q to the k, so you'll have leftover power of n minus k, where k is ranging from 0 to n. All right, so you have this expression. What you could do is look at the last term of that polynomial. So the coefficient Cn times p to the nth power. Notice how there's no q here because on the last term when k is equal to n, n minus n is 0. So the power of q turns out to be 0 on the last term. So you have this term, bring it to the other side of the equation, and then you can rewrite it this way. Okay, so negative Cn Pn is equal to the exact same polynomial, but you remove the last term, so k is only going from 0 to n minus 1 this time. But note that since k is only going up to n minus 1, the exponent of q to the n minus k, this is at least 1, right? Because there's no q to the 0th term anymore here. So you could take out 1 power of q from all of these expressions. But this means that on this right-hand side of the equation, you were able to factor out a q, so it's divisible by q. But if the right-hand side is divisible by q, then left-hand side is also divisible by q. So this expression is divisible by q. We know that p and q are relatively prime, so it was reduced to the lowest terms. So q must divide the other part, the coefficient Cn. So we get that q divides Cn. And you can kind of actually do the exact same argument with the very first term of this summation. So when k is equal to 0, the exponent of p is equal to 0. So the p factor is gone. And so you have c0 q to the nth power, this expression that you can bring to the other side. And every other term on the right will have at least 1 p in it. So the right-hand side is divisible by p, which means this expression is also divisible by p. And since p and q are relatively prime, that must mean that p divides the coefficient, the constant term C0. So that's how you can prove the rational zeros theorem. So if it wasn't clear, like what's amazing about this theorem is that it tells you if there is a rational solution. You have to assume that the rational solution exists before you can conclude these divisibility properties. So that actually kind of limits the possible form that rational number could take. So here's how you actually use the rational zeros theorem. So let's say you have a polynomial like this, x cubed minus 6 is equal to 0. And you're looking for roots of this. And you want to see if there's a nice rational number that you can plug it in, cube, and get 6. Well, if we use the rational zeros theorem, okay, if there happen to be a rational solution, the denominator has to divide the leading term, in which case this is just 1. So q has to divide 1, which means q is 1. And the numerator, p, has to be able to divide 6. So p divides 6. So there's a few possibilities there. P could be 1, 2, 3, or 6. And also we have to consider plus or minus everything. So these are all possible values of r it could be, right? 1, 2, 3, 6 are factors of 6, and the denominator has to be 1. And so, okay, there's 8 numbers to try. You can plug them all into this polynomial. None of them are actually roots. So there are no rational solutions to this polynomial. So you can conclude that, well, I mean, cube root of 6 is not rational. We eliminated all the possibilities except for finitely many, and you could just try them all out and just kind of exhaust all the possibilities. So if you run out of possible rational solutions, then the roots have to be irrational. So that's how this theorem is usually used. So you could use it to show that particular roots are irrational, or if it is rational, then there's really only few finitely many things you could try until you find it. So if there is one, you can find it very quickly. I hope that made sense. It's pretty cool theorem. Anyways, I think we'll end the video here. I'll see you guys next week.